Hi, everyone. My name is Maria, Beatriz, and I'm here to present to you a little bit about what I'm doing for my PhD project. I'm with Swansea University, and I'm working with the ALPHA experiment at CERN, and my project is entitled Sympathetic Cooling of Positrons with Beryllium Ions. So we work at ALPHA, where ALPHA stands for Anti-Hydrogen Laser Physics Apparatus. So as you can gather, we work with antimatter, specifically anti-hydrogen, and we shoot lasers at it, and we do things with it. Sorry. There we go. So before we turn it into more specific things, let's talk about what actually is antimatter. Some of you might have never heard of it. So antimatter is made of antiparticles, obviously, and these antiparticles theoretically will have the same mass as their matter counterparts, but they will have opposite charge and other opposite quantum numbers as well. Theoretically, we think that the same amount of matter and antimatter were formed right after the Big Bang or during the Big Bang. But the truth is, if you look around, if you touch things, everything is made of matter, even though there are little bits of antimatter around. For example, bananas create antimatter with the decay of, I think, potassium nuclei. They release positrons. So there are little bits everywhere, but they are significantly lower than that of matter. And what happens when you put matter together with antimatter is that they annihilate. So if we had exactly the same amounts of matter and antimatter at the beginning of the universe, why is it that we're made of matter right here? What happened? So the hypothesis is that something was different between those two things, but we don't know exactly what. And what we do at ALPHA is we investigate properties of antihydrogen, and we compare them with hydrogen atoms, and we try to look for these little differences. Specifically, we do laser spectroscopy, and we measure the difference between the energy in the first excited state and the ground state of antihydrogen. So there's an energy difference over there. And for hydrogen, we know that number up to 10 to the minus 15, so 15 decimal places. Very, very accurate. And at ALPHA, we can get the same number for antihydrogen to 10 to the minus 12. So we're very close, but not quite. And those 12 numbers are all the same. So we haven't found any asymmetries yet. But the goal is to get the same precision so that we can compare them as best as we can. Another thing that we're trying to do at ALPHA as well is to study the effects of the interaction of antimatter with gravity by sort of dropping it and see how it falls, basically. Measure G, the gravitational constant. So over here, this is where we're based. We're based at CERN in the antimatter factory, right here. The antiprotons are created when a proton beam hits a target and it releases antiprotons, and they're decelerated in the red circle here, DAD. This is not a scale, by the way. This is just a schematic. And then they're further decelerated in ELENA, and then ELENA sends them to us, ALPHA. There's many other experiments in this complex as well that are trying to do many different things. So this is where we are. And this is a drawing of our experiment. Now, this is the scale. This is the actual scheme of the experiment. So I'm sorry that it is a bit cluttered, but I'll do my best to try and explain it. So this is where ELENA gives us the antiprotons, or p-bars. I might refer to them as p-bars from now on. And I might refer to antihydrogen by h-bar. So if I do that accidentally, that's what that means. Bar means antiparticle. So the p-bars come from ELENA, and they're slowed down by a foil that we have over here. And they're caught in the catching trap. Now they're caught because we have a magnet called the Swansea magnet. And then we have electrodes that also create electrical fields. So basically we do a little well where we catch them with a wall on this side, and then we lift another wall, and they're bouncing around between those two electric field walls. And then the positrons are created here on the right from a sodium source. So it's a radioactive nuclide that decays and creates positrons, just like bananas. And then we send them to the two experiments that we have. We either send them to alpha 2 or to alpha G. So they meet inside of one of these traps, and we mix them, and we create antimatter. We can send lasers into both of these traps, and once we create anti-hydrogen, we can trap it using the magnetic fields. You might think that it is a little bit harder to trap a neutral particle because you can't use the electrical fields. But this is not about magnetic trapping, but that's a very interesting topic that you should read about if you're interested. We trap them, and then we do the experiments on them. Here is alpha 2 is where we do spectroscopy. Alpha G is where we do gravity. And here is just a drawing of the wells that we use to create the antihydrogen. So here in green, we have a few thousand p-bars, and in purple, we have a few million positrons. So p-bars are very scarce. There's not a lot of them. It's hard to actually get them to move around without losing them everywhere, because whatever they touch, they'll annihilate, they're gone. So we have very little of them, so we compensate by having a lot of positrons. We can have 14 million every 100 seconds, so we're good. So they're in these wells, and we slowly merge them together. And this is slow. This is in the order of a few seconds, and that's really slow for these kind of things. And we slow them down, and in step D, they're just about touching each other. And that's where it happens. That's where they're created, right? And then we get rid of these blue and red lines, and they just sit there until we let them go. And we let them go by turning the magnets off. So that's alpha. That's what we do there. What I do there is I work with beryllium. But why? You might ask. Beryllium is matter. What is it doing mixed with everything else? Well, we don't make a lot of antihydrogen. We make probably like about 20 antihydrogen atoms, every 10 minutes, which is really not a lot if you're trying to do an experiment that requires you to have 1,000 or so. It takes many hours. So there's always the urge to try and make this more effective, so we don't lose a bunch of things. One of the things that most influences the number of antihydrogen atoms that we make is the temperature of the positrons. So the colder they are, the more atoms we produce. So the goal is to get them as cold as possible. At the moment, we get them at 17 Kelvin just by cyclotron radiation. So that's when the positrons just move around in the magnetic fields and lose energy. They get to 17 Kelvin. But there's another technique to cool down these species, this species. And that is by mixing it with, in this case, beryllium, which is really, really cold because we use laser cooling to cool it down. And then when we mix them together, they sort of exchange kinetic energy and the positrons cool down. So this is sort of like if you have a glass of water at room temperature and you put ice, the ice will cool down the water. It's comparable to that. Why beryllium, you might ask? Well, it's a light species. The ions are really easy to produce. They're very easy to laser cool. Well, they're easy to laser cool. And the lighter the species, the better for this kinetic energy exchange. This is also possible to do because alpha already had a system to send lasers into the trap. So it made sense to actually try and implement this. So with beryllium ions, we can get the positrons down to 7 Kelvin. So that is more than double, more than half the temperature. So hopefully we could have a lot more antihydrogen atoms produced. Also, there's other very interesting things that we can do with beryllium, such as measuring the magnetic field using microwaves, for example. And that's also very useful because all of our experiments depend greatly on the magnetic field that we measure. So this is an inside look at the alpha 2 trap, which is where the magic happens. We have here in yellow, these are the electrodes. Each of these are electrically disconnected from one another. So you can apply specific currents to each of these electrodes and create whatever magnetic field you want, basically, within some limits. Obviously, you can't send 5,000 volts to everything. Within some limits, you can create whatever wells you want, and you can manipulate the plasma really, really well in there. And they are inside a liquid helium system. They are at 4 Kelvin. That's really, really cold. And they're surrounded by solenoids and mirrors. These are all types of magnets. And then for a big solenoid, which we call the Carlsberg solenoid, and that gives us a 1 Tesla field across the whole thing. And then with these smaller ones, we can get to up to 3 Tesla. Now here in blue, you can see the path of our on-axis laser. So we have 2 lasers for inside the trap. We have the on-axis, which you can see that it's parallel to the axis of the trap. So you can interact with the ions everywhere. This is a new addition. We just got it working a few months ago. It's very exciting because before we had this pink one, which you can see we call it off-axis because it really only interacts with the ions in the center of the trap over here. That's where they overlap the best. So we were confined to doing things there, and now we can do things wherever we want. Here on the right, you see the beryllium source. So this is how we produce beryllium. I will explain to you this process a little bit more in a few slides. And from the right here, we have the positrons, and they come from the positron accumulator that I showed you before. So this is the ablation setup. Here on the left, you have the mirrors and the laser setup that allows us to take the beam from the laser lab to the trap, and that's about 8-meter trajectory. So it's really hard to keep it aligned at all times. This is very, very sensitive to anything that happens. You can close a door too hard and it will mess it up. So it's very, very sensitive. You have to be very careful, but it comes out of this laser here and it reflects, it goes through a polarizer. So we take just a specific polarization and then it goes through a bunch of mirrors and it gets to the beryllium target. The beryllium target is zoomed in here at the bottom. You see it goes through this hole, hits the mirror, hits the beryllium, and then this ground plate is, this acceleration plate is given a voltage. So we create a potential difference here and we suck them out. And then they go into the trap. This is done by shooting very short, very high energy, well, very short and intense laser pulses into the target. So you just send one and it sort of vaporizes and ionizes the ions from the surface of the target. To do this, you need to have the right fluence. So fluence is just energy per area. So if you have a very, very tiny beam, you can have less energy, which is what we have. Our beam is 22 micrometers. It's very, very small, 10 to the minus 6. And our beam is usually 35 microjoules, so not very intense, but very small. And it just turns out that the fluence is just enough to ablate them. The reason we want to stay just above this fluence is because if we go higher than that or much higher than that, we will start creating B2 plus and B3 plus, which do not work for the laser cooling and what we want to do. And also we start ablating millions and millions of ions, and that's not what we want either, because we need to have some plasmas that we can use. Because when you ablate them, they are at thousands, 10,000 of Kelvin. They're very, very hot. And it's hard to trap them if they're hot and they're messy and they're just moving around. So that's what we want, just 500,000 ions with as little energy as possible. And here are some cool pictures. Here, this is beryllium ions that we image using an MCP. So this is actually a picture of the plasma as it hits a plate, a metal plate. When we take a picture. And here in the left, you see that this is a 35 microjoules, so just above gold. And we have a tiny plasma, and it doesn't look very messy. If you go only 15 microjoules above, it blows up. And it's just very hard to catch, very hard to manage. So this is sort of a game. And also, this is very sensitive, as I said before, about everything. You just have to make it as controlled as possible and isolated as possible. This is another cool picture. So this is what we call a stick. And this is a device that's vertically put outside of the traps. And they move up and down, and they give us whichever instrument we want. So here at the bottom, you can see that little box that I showed you a drawing of before. This is a beryllium target. Up here is the MCP, the thing we take a picture with, up here. And then we have some mirrors for the lasers to reflect off of. This is an electron gun. We actually make electrons very similarly to how we make beryllium, but without the laser. We just heat up this little bit of metal and then we suck them out. And then we have a pass-through, which is just things going through the stick. So I thought this was nice. This is also in high vacuum. So whenever we handle these types of things, we have to be very careful, wear gloves and sanitize everything. Now, laser cooling. I'm going to walk you through the physics of laser cooling, because I don't think many of you will be familiar with this. At least I didn't learn it in high school. So, so the idea that we can cool things down with lasers seems a bit strange, right? But this all stems from the fact that photons can interact with atoms and change their momentum. Again, this might seem strange. You think, oh, for something to make things faster or smaller, maybe it just needs to have a mass, but photons don't have mass. But that's okay, because they have energy and they have momentum, right? So this was proved in the early 1970s that they interact with atoms. And nowadays we can cool things up to near absolute zero. Really, millikelvin scale is very, very impressive. So how does it work? An atom has electron levels, right, with different energies. And you can make an electron go up and down those levels by making it interact with photons, right? And the way they do that is by either absorbing or emitting a photon. And the energy of this photon, so this is the expression for the energy of the photon, is exactly the difference between the excited state and the ground state, right? So if they're at the ground state and they absorb exactly this energy, they go up. And when they're not being interacted with, they come back down because they're not an infinite lifetime up here, right? So this is the expression for the photon momentum. So since photon has momentum, and there's this law of the conservation of momentum and the conservation of energy, if the atom absorbs the photon, right, that momentum has to go somewhere. And it goes exactly to the atom, so it changes, right? But this is still not enough to make it cool. It just changes it somehow. Let's see what else we need. So these red barriers over here, we can consider to be the walls of the well, right? So this is where we trap our beryllium, and they just dance around. And then we shoot a laser at it. And when they go towards the photons, their momentums will have opposite directions and they will slow down, right? They're sort of like hitting something head first, it will slow down a little bit. But if they're going away from the laser, the photon will make them go faster and they will heat them up. So since the atom is going towards the laser half of the time and away from the laser another half of the time, the net effect is zero. So the net effect on the temperature is nothing happens, okay? So the net momentum will be zero if the laser is exactly at resonance. By the way, when I say resonance, I mean when the laser has exactly this wavelength that we need to do the transition, okay? So at resonance means that it matches the parameter that we want. So now we take advantage of a thing that you definitely heard of in AstroCamp, the Doppler shift. So Doppler shift is when an object is moving either towards or away a source of radiation, and they perceive the wavelength to be either red shifted or blue shifted, right? So if you're moving towards the radiation, you see a higher frequency, so a lower wavelength. If you're moving away, it'll be the opposite. So what we do is we shift the frequency of our laser a tiny bit, right? We shift it towards the red. So we make it a little bit longer so that if the atom is going towards the light, it will see it shorter as we want at resonance. And if it's moving away from the light, it will see it even longer away from the resonance. So there will be no interaction, right? So the atoms that are moving away from the light don't even interact with the photons. And the ones that are moving towards it will, some of them will see it at just the right wavelength and they will interact. So this is how we get them to slow down and to be cooler, right? So the net effect here will be negative in terms of temperature, will go down. And how far will it go down? So we have the Doppler limit. So this is sort of how cold we can get it. And it's in the order of millikelvin. Gamma here is the line width of the transition. What this means is that resonance is not a delta function. It's not a either 0 probability or 100% probability. It's a curve. It's a sort of a Gaussian curve, right? So it will be maximum at resonance, and there will be a slight little range of frequencies that would also allow it to interact with the atom. But that's very, very small. For beryllium, it's the 19.6 megahertz. Very, very tiny. And I'll show you how tiny it is because for laser cooling of beryllium, we use a 313 nanometer laser, which corresponds to 957. Sorry, I don't know if you can hear that. That's my dog. I'm so sorry. Corresponds to 957 terahertz. And the line width is 19.6 megahertz. So tera 10 to the 12, megahertz 10 to the 6. It's a tiny compared to the actual wavelength of the laser. And this shift is also really small. We usually shift it by 200 megahertz to cause, this is enough to cause this Doppler shift to be relevant. So this is a laser cooling. But how does it actually work? What transitions happen? So here on the left part of this image, you have the electron levels of the beryllium atom, right? And this is normal. You've probably heard of it in school, the 2s, 1s, all those. And this is fine at 0 Tesla. No magnetic field is happening here. That's what they look like. When you put them in a magnetic field, there's this effect called the Zeeman shift, and they separate from each other. So it creates more energy levels, right? There are just many more, and the electrons will populate these different levels. So the ones that we use for cooling are the ones on this level, and we cool them up to P3 halves, and then they come back down and they go through that cycle. Here on the right, you can see an actual accurate plot of the energy levels as a function of magnetic field. So at 0, they're just 2, and then as you go, they separate and they become further away from each other. So this is at low fields, and here is an example, is a plot of the fields that we actually care about, which at alpha are 1 Tesla and 3 Tesla. So you can see the stronger the magnetic field, the more they'll be shifted from the original level. So we have to adjust the frequency of our laser related to this magnetic field. That's why we have 2 lasers as well, because we can have one laser tuned at 1 Tesla and another laser tuned at 3 Tesla. So this is the laser cooling part. And now I'm going to show you more cool pictures of the different stages of beryllium. So how do we start? We start with ablation. You've seen this already. Little blob, very, very hot and very hard to tame. Then we trap it and the blob sort of expands. And then we laser cool it. And we don't really understand this shape. This is something that we're still studying, but it definitely interacted with the laser. And this final plasma here is at about 120 Kelvin. So not as cold as, but we also, this was just a test. We weren't really trying to get it as cool as possible. But 100 Kelvin is pretty cool, 120. So these are the different stages of beryllium in alpha. Now, the actual title of my talk, sympathetic cooling. So some species cannot be laser cooled, for example, the positron. And sympathetic cooling is the process through which we put 2 different species together and they exchange kinetic energy through Coulomb interactions. So they're both charged particles, E plus, Be plus. And this exchange of energies causes the hotter species to cool down. This is not only done with positrons, we actually do it to slow down and to cool down the antiprotons. Here on this picture, you see this big green circle, that's electrons, that's millions of electrons. And here, this sort of halo is antiprotons, actually. And you might ask yourselves, why are they hollow? Well, when things sympathetically cool, there's an actual spatial separation. So we have the heavier species will go outside and have sort of a donut shape. And then the smaller species will go inside and have very, very dense center. So this is this image that we see here. We actually moved them and imaged them right after they were cooled. So we do this in many places in alpha, but with beryllium, it's a bit more complicated because it has to be compatible with everything else that's going on. And that's the main challenge now. So we have cooled down positrons, but it takes about 10 minutes and we need it to be faster because we need it to be about 2 or 3 minutes. So that's what we're working on right now. So these are the electric wells that show how they merge. In blue, you see how it starts. And then in dotted line, you see how it ends. So we have 2 wells and we lower one of them and we sort of dunk the positrons into the beryllium slowly and they merge and they interact and they stay there until we are satisfied with the temperature of the positrons. So here, this plot shows the positron of the temperature versus the final laser detuning. In saying final laser detuning, that's the same as saying beryllium temperature, because the closest you are to resonance, the colder it'll be. So 0 is resonance, and you can see that we're very close here, and that's the coldest positrons we get, right? We get about 7 Kelvin. Now, after resonance, the temperature shoots straight up. And if you think about what I said before about the Doppler shift, when you go past this the resonance, you start blue shifting the laser rather than red shifting. So you just start heating them up instead of cooling them down. So we have to be very careful. We cannot be too greedy because if we go too close to 0, they just shoot right up. So you have to sort of balance these 2 things. So to finalize my talk, what's next? We have to make this technique compatible with antihydrogen. As I said, we need to make it faster. And we actually need to make antihydrogen with sympathetically cooled positrons and see that the numbers increase. Another fun things we can do, as I said in the beginning, is to implement things such as magnetometry using beryllium ions. So thank you very much. That was my talk. If you have any questions, feel free to ask them or to send them to Discord. I will answer them, hopefully.